Welcome to Module 3, How to Read an EKG, Systematic Approach. Let's get started. I want to start off with a little bit of a disclaimer here. By no means am I trying to say that there is only one method to analyze an EKG. This is the method that I was trained in. However, if there is a method that you know that works for you, please stick to that. The most important thing when approaching an EKG is that you approach it in a systematic way, the same way every single time, so that you don't miss anything and you can do a very thorough job. All right, let's get started. We're going to start with heart rate. We're going to look at the distance between the R to R interval. We're going to determine if the heart rate is normal or abnormal. Normal heart rates are between 60 and 100 beats per minute, as we know. And we can determine this via 3 different methods. First is our small box method. If we remember that one of these small boxes equal to 0.04 seconds, and a large box is equal to 0.2 seconds. So if we take 1500 divided by the number of small boxes, that'll give us the unit of BPM. And the same thing, if we take 300 divided by the number of large boxes, that'll also get us to that unit of BPM. The last method here is our 6-second method. And if we count out 30 of these large boxes, as is in this strip here, that is 6 seconds of time. And so we can actually just count the number of full R peaks that are within that strip, and that'll give us an estimate for the heart rate. So we'll start with that one. We've got 1, 2, 3, 4, 5, 6, 7, 8 different R complexes. That'll give us 80 beats per minute. Okay, now we can look at our small box method. If we mark this R peak and that R peak, and we count the number of small boxes in between, that's 5, 10, 15, 16, 17, 18, 19, 20 small boxes. And we also have 1, 2, 3, 4 large boxes. If we take that 1500 divided by 20, that'll give us 75 beats per minute. And the same sort of way, if we did 300 by 4, that would also give us that 75 beats per minute. Okay, so those are the different ways that we can look at heart rate. A couple of pro tips for you over here, right? I like to remember that 3 to 5 large boxes is 100 to 60 beats per minute, respectively. So if I were to mark out 3 large boxes and 5 large boxes, I know that if it is less than 3, it's tachycardic, and if it's greater than 5, it's bradycardic. And that's just how I've always remembered it. Another way that people tend to approach this is by memorizing this number pattern. We have 300, 150, 100, 75, 60, 50, 43, 38. So you know if you start here at this R peak, and the next one is 1 large box apart, that it would be 300 beats per minute. If it's 2 apart, that's 150. 3 apart gives us 100, 4 is 75, and so on, so forth. All right, then we have rhythm. With rhythm, we are looking at the pattern of the R to R interval. We want to determine, is this regular or irregular? So a regular rhythm, we're going to see that these R to R intervals are the same distance going across the strip. It's 20 small boxes here, and it's still 20 small boxes over there. If it was irregular, we might go 20 to 15 to 24, or et cetera, et cetera. It would just not be the same number, equidistant one from another. Now, irregular, we can denote into 2 categories. We have regularly irregular and irregularly irregular. Now, regularly irregular is going to be a patterned approach. It won't be regular because not every single R to R interval is going to be equal to each other, but it's going to be patterned in a regular pattern. So let's say we have 1, 2, 3 and a gap, and then 1, 2, 3 and a gap, and then 1, 2, and 3. So you can see that the distance between these guys is relatively, minus my art skills, consistent across the page. And the distance from these gaps is also relatively consistent. So we have this patterned approach. It's not regularly, but it is regularly irregular. Now, irregularly irregular, this is going to be your buzzword for AFib. When you think of irregularly irregular, I want you to think of AFib first. We see it all of the time used in different STEM questions. That is your go-to. But the point here is there's no rhyme or reason. There's no pattern. It's just plain irregular. It's irregularly irregular. All right. We spent a lot of time in Module 2 talking about axis, so I'm not going to go into depth there again. Go back to Mod 2 if you need to review it. But I do want to talk about V-lead transition. Remember, our V-leads, we are going from V1 on the right side to V6 on the left side. This is our precordial leads. They take a transverse section of the heart. Okay, so what we would expect to see is on the right side of the heart, we want a negative QRS complex. We want a negative deflection because we expect the signal to be away from the bulk of the flow that we would expect it to be going. It's going in the opposite direction, so we should have a negative deflection. And then when we get to the left side, it should be a positive deflection because it is going the direction that we expect it to go. Anything in this V3, V4 range, we consider to be normal. Now, if you have something that is V2 or earlier, we would denote this as early. And if you have something that is V5 or later, we would denote that as late V-lead transition. Then we have our intervals. Intervals we measure across the x-axis. So let's go ahead and start with our PR interval. All right, so PR interval starts at the start of the P wave and ends at the start of the QRS complex. So if we zoom in here, we start at the start of the P wave and we end at the start of the QRS complex, and we count in between. We have 1, 2, 3.5. 3.5 times 0.04 is going to give us 0.14 seconds. And if we go and verify this, 0.12 to 0.20 is going to be our normal, so we are within normal for that. The next one we have is our QRS complex. So we can measure the start of the QRS complex here and the end of the QRS complex here, and we can count the number of boxes in between. That's 2.5. 2.5 times the 0.04 seconds is going to give us 0.10 seconds. And again, if we went and verify, 0.08 to 0.12 is going to be our normal, so this would be a normal QRS complex. And the last one is the QT. So if we start at the start of the QRS complex here for QT, and we go all the way to the end of the T wave, count in between, that's 5, 6, 7, 8, 9. 9 times our 0.04 is going to give us 0.36 seconds, and that is within our normal of 0.36 to 0.44. Morphology is a little bit of a catch-all. It's looking at the shape of the waves and the segments. So is the P wave nice and round? Is it a nice little hump? Are there extra? We expect a 1-to-1 ratio. If there are more P waves in QRS complexes or vice versa, then we have to investigate further. Does the QRS complex have multiple R peaks? Or does it have delta waves where we see this slur into the QRS complex? Is the amplitude normal? Are there extra QRS complexes that shouldn't be there? Is the ST segment flat? Do we see less than 1 millimeter variation in the J point in contiguous leads? Is the T wave smooth? Is it biphasic? Is it tall in relation and peaked in relation to R? These are all things that we want to look at, and it can be challenging because there's no one list that's going to be like a check off of everything you need to look for on an EKG. So what I want you to do is get very comfortable with recognizing what normal looks like. Now, obviously, this example that we have here is a computer generation. So it's, the most normal of normal that you could possibly get because it's not even a real person. It's not quite going to look like what your live patients might, right? But that said, this is a very good example of what the most normal of normal can look like. And I want you to be familiar and know what these different intervals and what these different waveforms look like on a normal patient, so that when you get an EKG that is abnormal, you're able to recognize that looks different, that looks funky, that looks weird, and now I want to investigate. And that is the key with EKGs. We say, hey, that looks weird, now I'm going to investigate and try and figure out what that means. I did want to give you a little bit of an intro with QRS complexes as well. When we go through naming of QRS complexes, it can be a little bit interesting just in the sense that there are lots of variations of QRS. So when you have your isoelectric line from your PR side, right, you've got the first deflection down, if not preceded by a deflection up, is always going to be your Q wave. Now, if you've got your isoelectric line and your first deflection is up, this is going to be an R. The second deflection down after a deflection up is always going to be your S. And whether or not it's a lowercase or an uppercase letter is really just based off the size of the waveform. Now, if you had isoelectric and then something up and something down, this would be an RS. Or if you had here, down, up, this would be a QR. So there are lots of different variations of this. I just wanted to give you a little info so that you know that there are different things that can exist. All right, electrolyte abnormalities. For hyperkalemia, we can have these really tall peaked waves here for hyperkalemia. And then for hypokalemia, we can get these U waves. And they're down here. They're these little guys that typically come after the T wave. It's like an extra little bump. And then for hypocalcemia, we see our prolonged QT interval. And for hypercalcemia, we see a shortened QT interval from here to here. Then we have our biphasic P wave. This obviously is not what we would expect to see as normal. Our normal P wave is going to be this nice pretty lump over here. If we start to see it being biphasic, we're going to say, well, we want to think about mitral valve stenosis for that, which is a splitting of the atria. If we think about just our normal P wave in general, the first half of this is by one atria, and the second half of this is the other atria. So if we see these two atria start to split, that means that there's something going on. And that's where we look at that mitral valve stenosis, or splitting of the atria into two distinct waves. Then we have our left ventricular hypertrophy. Two different methods that I put here that you can look at this. There's more than one way to do it. I learned on the second method, but you do what works for you. So I would approach it as S wave in V1 plus the R wave in V5 or V6, whichever is larger. If it's greater than 35, I'm going to consider that a positive test for left ventricular hypertrophy. And then for right ventricular hypertrophy, if the R to S ratio is greater than 1 in lead V1, or the R wave in V1 is greater than 7, we would also consider that a positive sign. All right, let's do a practice problem. And I put the little guide over here for you guys as well, so that you can follow along. But I really want to approach this and kind of talk it out how, to the T, how I would approach an EKG. So the first thing I'm going to look at is the speed of the paper. It's the standard 25 millimeters per second. And then I'm going to see that this is 10 millimeters per millivolt, which is also denoted by this box here. The next point that I'm going to notice is that we have V1 for our rhythm strip. Remember, any of the leads can be present on your rhythm strip, but it is important that you know which one it is so that you know if it looks normal or abnormal for what you would expect to see. All right, so we're going to start with rate. So we can pick an R to R interval here. Let's say here to here. And we've got 5, 10, 15, 20. That's 21, 22, 23, 24 small boxes. So 1,500 divided by 24 small boxes is 62.5. So let's say that's 62 beats per minute. Okay? So we are going to say it's 62 beats per minute, which is normal. The next thing we're going to do is rhythm. Rhythm, we're going to look at the distance from R to R. So if we look at our rhythm going across here, we're going to say that these look relatively the same. If we were to count out here, we would see another 24 small boxes. And so our rhythm, we're going to say, is regular. QRS Axis. If we're looking first, remember there's two different methods to do this. We have either the isoelectric line, or you can look at the quadrant method. The quadrant method isn't going to be super helpful here because our most isoelectric line is our AVF. So if we take our clock face here, AVF is the most isoelectric. Here. And so 90 degrees from AVF is going this way, and we're going to go towards the positive side, lead 1. So our degree for QRS Axis is 0 degrees. And then our V-lead transition, we're going to see here. All right, so right away, we should notice that this is looking a little bit abnormal. So if we look at and mark, this is our isoelectric line. We've got 1, 2, 3, roughly 3 boxes going up. And from the isoelectric line, roughly 1, 2, 3 boxes going down, roughly. So our V-lead transition is actually happening in lead V1. So this is super early of a V-lead transition. All right, next step, we're going to look at our intervals. And we're going to do PR, QRS, and our QT intervals. Now, when you look at an EKG, I want you to pick the best example for what you need to use. So when I'm looking for a really good PR interval, I'm not going to use this guy because it's not clear enough where that P wave is in relation to the QRS complex. I wouldn't want to use any of the ones that are even remotely unclear. So I'm going to choose this guy for my PR. We're going to mark the beginning of our P wave all the way to that QRS complex. Okay, and this is 1, 2, 3, 4, 5, roughly 6 small boxes, which gets us 0.24 seconds. Now, this is actually long. Remember, our normal is 0.12 to 0.20 seconds. So this is long. Now we're going to look for a nice QRS complex. Let's choose this guy over here. Okay. We're going to go ahead and mark the beginning, mark the end. That's about 1, 2, 3 small boxes, which will give us 0.12 seconds for our QRS axis, complex interval. And then lastly, our QT. We're going to pick a nice example again. We can even use this guy over here for our QT. Here, all the way to the end of the T. Okay, and we've got 5, 6, 7, 8, 9, 10, which will give us 0.40 seconds for our QT. All right, and then we go into morphologies. Do we have one P wave for every single QRS complex? Well, it looks like, yes, we have a 1-to-1, a 1-to-1, 1-to-1, so on and so forth. So our P waves are good. Our QRS complex are a little bit interesting. We're noticing that these maybe look a little funky over here, and that we know our V-lead transition in general is earlier than we would expect it to be. But otherwise, our morphology of the QRS complexes look okay. If we look at our ST segments, are our ST segments all level or flat? Looking across, starting at lead 1 and going across. Our ST segments overall look okay. We can see how we have an isoelectric line and we stay on the other side, even if it looks a little funky from the distance. We're still meeting that. Do we have any T waves or U waves present? Or sorry, peak T waves or T wave abnormalities or U waves. Remember, with AVR, we expect AVR to be negative, so that would be normal. Same with V1. So morphologically, we're not noticing anything that's too bad here. So we're going to say morphology is okay overall. So if we were to sum up this entire EKG, the one thing that I'd want to note is that our V-lead transition is early and that we're seeing a long PR interval. And we're going to talk about in other videos what some of the things that this might mean, but this is generally how you would approach an EKG from start to finish. Hope this was helpful for you. Looking forward to the next module. Take care.